So in the last class, we began discussing structures. So like I said, a structure is a heterogeneous derived data type. It is a complex data type, but a heterogeneous one. An array can store values only of the same kind, whereas a structure can store values of different kinds, int, char, float, and so on. And we also took an example of say we have some 100 students in the class, and each student has multiple attributes like name, age, ID, address, and so on. Now, how to store this data? One way is to sort of split it horizontally. Like you have an array of names, array of ages, array of IDs, and so on. But that is an unnatural way of storing the data and also dealing with the data. It is because naturally for us, a student is one unit, one entity, one object. So it is more natural if we store the data of an entire student together, right? So rather than splitting it horizontally, we can split it vertically. Like each student is one unit. So store all the students' attributes at one place. So that unit is called a struct or an object. Okay. So we looked at that, and I also told you that struct or any user-defined data type has three steps: definition, declaration, and initialization. Because it is user-defined, you need to use the definition as well. If it is inbuilt, you just need to declare it and initialize it. You need not define it, right? And among this definition, declaration, initialization, it's our choice. Either we give these three completely separately, or we combine steps 1 and 2, or steps 2 and 3, or we combine all the three steps. That also I showed. So struct definition is quite simple. You just give a name like struct student or struct university or anything. Struct is the keyword, and then you give a name to that struct. So this name is basically called a tag name. So this struct is actually struct student, right? There can be a different struct university, struct employee, struct teacher, different struct objects you can build. Each of those words which come after struct, those are called tag names. All right, and we just gave some 4 attributes. So these are called attributes or members. Usually, some use members, some use the word attributes. I prefer to use the word attributes. So it depends on the use case. In this case, these seem like attributes of a student, but in some other case, like struct point, their x and y, they are 2 coordinates. So those seem to be like members of the point rather than attributes of a point. So depending, it varies from case to case. Any word is fine. So there are attributes or members in a struct, and this struct is like a class, right? It is just giving the basic structure of any student, not this student or that student, but of any student. Any student will have these 4 attributes. All right. So since this is not referring to any particular student, these attributes should not be initialized in the struct definition itself. Initializing means what? You give a specific value to a name, you give a specific value to an age, you give a specific value to height, ID. If you give specific values, it refers to a specific student. But this is not anything specific. This is a class. So that's the difference between a universal and a particular. If once you initialize, it points to a particular student, right? But since this is a class, this is a universal kind of thing, it should not be initialized. You cannot even initialize it. If you try to give values in the struct definition itself, if you try to give values to these attributes, maybe some name and some number for the age, some number for the height, some ID, if you initialize them like that, it will give an error because it is not a particular student. It is struct class itself. So you cannot initialize struct class members. Only after instantiating it, like student S1, S2, S3. For each of these students, you can initialize. S1's name is this, S1's age is this, S2's name is this, S2's ID is this, like that. So you can initialize only the instances, not the class itself. All right. So keep that distinction in mind. So this is definition. And then second step is declaration. I defined a data type called struct student. Now I am instantiating it. I am creating some instances of this class like this, like struct student S1, S2, S3. This is like int XYZ. Simple. I can also combine these two steps, definition and declaration. In this case, I gave them separately. Here, I am combining them. So how do we combine? You just give the definition. This is the definition part, and then list the instances immediately. So definition and then variables or instances S1, S2, S3. So here we are combining both definition and declaration. All right. And the third step is initialization. So initialization means once you have instances, for each instance, for each attribute, you give a value. S1 is an instance, S2 is an instance, S3 is an instance. So take S1 and populate its attributes. Take S2 and populate its attributes. Take S3 and populate its attributes. That's what we are doing. So S1 means like student 1. His name is Ravi, age is 17, height is so and so, ID is so and so. This is initializing that student. You again initialize another student, and so on. Okay. You initialize instances of a struct. You don't initialize struct itself. Okay. So this is initialization. Now we can combine declaration and initialization as well. That is, I say struct student S1, I declared S1. At the same time, I am giving values to this. I am initializing this. Okay, so I can combine declaration and initialization. In the previous case, initialization is done separately. But in this case, declaration and initialization are combined. If they are combined, you can give the values like this in the form of an array. If they are not combined, you cannot give the values in the form of an array. You have to declare member by member. That's what we did here. Here, we declared each member separately because here initialization is separate from declaration. Okay. And we can combine all three also. Definition, declaration, and initialization. Like this is an example here. Struct student definition is given and S1 is declared and S1 is also initialized in the same step. S2 and S3 are just declared. They are not initialized. They are not given any values. Their members are not populated. Okay. So it's up to you. You can combine, you can split, you can combine two steps, you can combine all three steps, or you can separate all three steps. It's up to you. All right. Then we looked at example of a point, struct point. So struct point is quite simple. You just have each point has two coordinates, x and y coordinate. So you just say float x comma y, x coordinate, y coordinate. All right. Now this is a structure. Now you create instances of this struct point, P1, P2, P3, and so on. Here we created 6 points, 6 instances. And I showed you different ways of initializing these points. In the first way is you just list the values of the attributes in order. This is one way. So 4 comma 1 means x is 4, y is 1. P2 I didn't initialize. I just declared. P3 I initialized, but in a slightly different way. I first initialized y value and then I initialized x value. But since I am changing the order, I need to specify the attribute name. If I am not specifying the attribute name, then I need to give an order. Okay. If I don't want to follow the order, then I need to specify the attribute name. Y is this, x is this, right? And suppose if I know only few attributes, not all the attributes, I only know y value right now. I don't know the x value, I'll give it later. So that is also allowed. This is designated initialization. If you are naming the attributes and the value side by side, that is called designated initialization. If you are not naming the attributes, it is just, you just need to follow the order. Order matters there. In designated initialization, order does not matter, and also it need not be complete. All right. And even in this other case where it is not designated initialization, it need not be complete, but order still matters. Like in this case, we just gave one value, but you did not tell whether this value is of x or of y. But since you did not name the attribute, it will automatically assign it to x because x comes first in the list of attributes. This is very similar to array initialization. If your array has 10 values, but you are assigning only 4 values to it, the first 4 values, these 4 values are assigned to the first 4 elements of the array. The remaining 6 elements are initialized to 0. Right? Similarly here, if you have say some 5 attributes, if you are giving only 2 values, those 2 values will be assigned to the first 2 attributes by default. All right. If you want them to be assigned to specific attributes, say 3rd and 5th, then you give designated initialization, give the 3rd attribute name equal to this, 5th attribute name equal to this, like that. Okay. And remaining values we initialized in the program. We cannot use this kind of initialization because this is separate from declaration. If you separate initialization from declaration, you cannot initialize like this. You have to initialize member by member, right? And then we looked at a new keyword called typedef. So typedef, it gives an alias for a keyword. This keyword is usually a data type, like an int or like struct point. We want to shorten it. We are shortening it or giving it an alias called point, something like that, right? Say one example of typedef alias is, so I can say typedef int. I can say give it a different name, capital integer. So it's not necessary that this one is always shorter than this. Its purpose may be different. Yeah, please maintain silence. You're constantly disturbing me. So this is an example where instead of using int, I can use this word capital integer. Why? So what may be the use case? You see, depending on the architecture, in some systems, int is 4 bytes. In some other systems, long int is 4 bytes. Now, suppose I wrote my program specifically for a 4-byte integer. In one system, it may be int. In another system, it may be long int. So if I write my code with whatever, if I use int in my code, int x, int y, all this, and I'm declaring all the variables using this keyword int, then when I move to the other system, this will be of 2 bytes and long int will be of 4 bytes, which means I need to replace this with long int. So wherever I use int, anywhere in my code, I need to look at all those instances and replace all those int instances with long int, right? Instead of that, I will give an alias to int. I'll call it integer. So instead of using this int here, I will say integer. All right. So whenever I want to declare an integer variable, I will say integer x, integer y, integer z, and so on. So my code will have only the word integer. It will not have int. There is only this one line where int comes. All right. So when I move to a different system where long int is of 4 bytes, I will just replace this word int with long int. Long int or long, anything will work. Long means long int. So this code need not change. It will still remain integer, but here integer means long int. In my system, integer means int. Right? I only need to change this one line in the other system. I need not touch this code. Got it? So that is like a completely user-defined word which does the job. You need not worry about when you move to a different system. You need not worry about looking at each instance of int and replacing it with long. All right. So you use a common word, integer, capital integer, and you in the typedef statement you just make that single change when you change the system. That's it. Okay. So this is an example where alias is useful. Similarly, in the cases of struct, when you're using typedef with struct some tag name, it is just to make our job easier. Instead of saying struct point p1, struct point p2, struct point p3, we just give it a shortcut. It can be just say point, or you can shorten it further. You just say maybe say pt. So instead of saying struct point p1, p2, p3, I'll just say pt, p1, p2, p3. So pt means struct point. That's all. So this is a shortened form of struct point, like that. Okay. So let's look at an example. So I'll say struct point float x comma y. So here I will write type def pt. So here pt is the alias for struct point. pt is not an instance of struct point. If this type def word is not there, then pt becomes an instance of struct point like p1, p2, p3. But since type def word is there, pt becomes an alias. It is not an instance. Okay. So in int main, you can declare points p1, p2, and so on. Okay. So here I'll just say p1 equal to 1, 2, p2 equal to 3, 4, whatever. Now again it's normal. Print p1.x, p1.y. Same thing. Okay, this is p2.x and p2.y. All right. That's it. 1, 2, 3, 4. So here I did not use struct point. I just used pt, but it worked because pt is an alias for struct point. All right. So this is one method. Second method is you first define the point and then write this type def statement separately. Okay, anything is fine. Either you give type def along with the struct definition, or you define struct as usual and then you give the alias separately. Anything will work. All right. Okay, so let me just run and show it. Okay, now, all right. So now we can move on to building complex structures. Like point itself is a structure and point is a geometric concept. Can you think of a higher order geometric concept, or what more complex geometric structure can you build after point? What comes after point? Line. Line is made up of points. And what are the minimally how many points you need to define a line segment? 2 points. So now I can create a new struct line segment. What will be the members of this struct? Like I said, we minimally what do we need to define a line segment? 2 points. X1, Y1, X2, Y2, right? But X1, Y1, X2, Y2, are they independent elements, or X1, Y1 mean something? X1, Y1, 1 unit. It is what? 1 point. So instead of treating X1, Y1, X2, Y2 as 4 elements, we can treat X1, Y1 as 1 point, X2, Y2 as 1 point. So we can directly have points themselves as members of this line segment, right? So assume struct point is already defined. So struct point is already defined, and we also gave it a shortcut. point, or shortened it as point, alias. Now, what will be the members of this line segment? Ah, 2 points. How to write that? Sorry. Point P1, P2. That's it. So points themselves are the members of this struct. In the previous case, in that struct, float were the members. In some other struct, int, char, they were members. In this struct, another struct itself is a member. But no struct can have itself as a member, or an instance of itself as a member. A line segment struct can have a struct point as member, but a struct line segment cannot have struct line segment as a member. A struct point cannot have struct point as a member, because that will sort of lead to infinite regress. Okay, you cannot define a structure then. All right. So for this also we can give an alias. We can say type def struct line segment. Let's call it just a line. Okay. Now, so let me show an example code. Remove this. So we have struct point. We are calling it PT. Alias is PT. And then I define struct line segment and PT, P1, P2, right? We also give the alias for line segment, type def struct line segment. You are giving the alias line. All right. So now so line itself will have instances, right? So I can create line L1, L2, L3, and so on, right? Now I will initialize, say, L2. Okay. Now L2 is, how many members it has? 2 members. Each member itself has 2 members, right? P1 has 2 members, P2 has 2 members. So you can write it as, so this is P1, this is P2. You give some numbers 1, 2, 2, 3, right? So this is like a 2D array in some sense. Okay. So I initialized L1, I initialized L2. Now we need to initialize L1 and L3. Now how do we initialize L1? Suppose L1's points, P1 is 0, P2 is -1, 0. L1 dot P1 dot X, right? I cannot say L1 equal to so and so, right? If I give like this, will it work? No, because initialization is separated from declaration. Now it will no longer work. Can I say L1 dot P1 equal to so and so? No, this will also not work, because here also P1 initialization is separated from P1 declaration. So this will also not work. So you have to go to the smallest element wise initialization. So that is L1.P1.x, L1.P1.y, L1.P2.x, L1.P2.y. Each of these members you have to declare, you have to initialize separately. Say this is 0. Now let me copy it. L1.P1.y, L1.P2.x, L1.P2.y. Say this is 1, this is -1. All right. So this is one way of initializing. Sorry. No, L1 has 2 points. L3, now we will say, we will scan the values from the user. All right. So scan f %f %f. What should I write here? ampersand L3 dot P1 dot X ampersand L3 dot P1 dot Y ampersand L3 dot P2 dot X ampersand L3 dot P2 dot Y. Okay, and then we will print all these points. So we will say L1 equal to this is point P1, two values, percentage 0.1F, comma percentage 0.1F. Same thing here. And here what should I write? L1 dot P1 dot X, L1 dot P1 dot Y, then L1 dot P2 dot X, L1 dot P2 dot Y. So let's copy paste this for the other two lines. In this line, everything is changed to L2. In this line, we'll change everything to L3. Okay. Fine. See. So first, we need to give the points of L3. Let's say 1, 2, 3, 4. L3 we are scanning. Okay. So now done. L1 we gave in the code separately. L2 we gave during declaration itself. L3 we gave we took as input from the user. 1, 2, 3, 4 I gave, so it gave 1, 2, 3, 4. Okay, fine. All right. Now coming back to the okay, before that, so let me copy this. You see, in this case, struct point is defined outside struct line segment. Struct point is an independent struct, right? We can also define struct point inside struct line segment, right? So let me so this is what is this doing? Here you are defining struct point inside line segment, and you are also declaring instances of struct point P1 and P2, and you are saying those instances constitute the members of struct line segment, right? This will also work. This will also work. Now the rest of the code is same. Let's check that. Okay, but now the thing is, since we defined struct point inside struct line segment, you may think that we cannot access struct point outside the scope of struct line segment. It is visible only inside struct line segment. You may be thinking that. That's a proper way of thinking from whatever we learned about scope of variables. You remember, if I declare a variable inside a scope, scope means what? A block. Block means what? Two curly brackets. Anything declared inside that block is visible only inside that block. If you declare a variable inside that block, that variable is not visible outside that block. Okay. Same thing, you may think that if I define a struct inside this block, this struct is not accessible outside this block. But it so happens that struct is an exception for that. If you define a struct inside a struct, even then the inner struct is visible outside the outer struct. So here struct point is visible outside struct line segment. Although struct point is defined inside the block of struct line segment. Okay, so you can actually declare struct point P1, P2. This will work. So struct is an exception. Struct's members are not accessible. Struct defined inside another struct is accessible. Okay. So this will work. And these 2 points P1, P2 are different from the points of L1, L2, L3. So L1.P1 is different from this P1. L1.P2 is different from this P1. P2, this P2. Okay. So if you give any values to these points, they are like independent points. They have nothing to do any line segment. Okay. That much is there, but struct is a struct defined inside another struct is still visible. All right. But you cannot define a function inside a struct. That is the fundamental difference between a struct and a class. In object-oriented programming, later when you learn classes, or if some of you have experience with Python, you might have used something called a method with an object, say array.length, string.length, this dot function, dot some method. That is basically saying this length is a method inside the object called array or inside the object called string. Okay. So those are functions defined inside the object, defined inside a class. But inside a struct, you cannot define a function. You can only define a function inside a class, not a struct. Okay. Inside a struct, you can only define members, either some variables or other structs. That's all. Okay. So this is something to keep in mind. All right. Now let's yeah, coming back to the initial problem that we asked. Say we have 100 students. Now each student has say 4 attributes. Now what we decided is we will store each student's data as one unit. All 4 attributes as one struct, one object. But at the same time, I want to store all the students' data together. So a simple way is you first create a struct for each student and then create an array of these structs. Rather than creating an array for name, array for age, array for IDs, you create an array of entire structs. Okay. And then you can access each student and each element of each student easily. So like how do you declare an array of size 100 integer array? You say int, say a of 100. Similarly, instead of int, you just want to declare an array of 100 struct students. So what do? You just replace this with struct student. That's it. So earlier, what did we do? We said struct student S1, S2, S3. But if we have 100 students or 1000 students or million students, we need to create million variables. Instead of that, you just create an array like this. So now A of 0 means first student, A of 1 means second student, A of 2 means third student, and so on. A of 99 is 100th student. So instead of S1, S2, S3, you are using this. So now for each, say I want for the third student, I want to access the details. A of 2's name, something, say Anil. A of 2's age, say 19, whatever. So this is how I can initialize each struct. Instead of saying s1.name, s1.age, now I am saying a of 2.name, a of 2.age, a of 2.id, and so on. A of 0.name, a of 0.age, a of 0.id, and so on. That's all. So each student is a struct, and using the dot operator, I can access individual attributes of that struct. That's all. Fine. All right. Next, how do you copy one struct to another struct? You see, actually copying one struct to another is extremely simple. It's not as complex as arrays. How do you copy one array to another? You have to copy element by element. You have to run a for loop and you copy element by element, each element at a time. You cannot directly say array 2 equal to array 1. You cannot say that, right? You have to copy a of 0, a of 0 to b of 0, a of 1 to b of 1, and so on. So you can't copy a to b directly. But if you have two structs, copying one struct to another is as simple as copying one integer to another. So if you have say two integers, say int x equal to 5 and y, you can just say y equal to x. It just copies the value of x to y. Similarly, if you have two struct points p1 and p2, and let's say p1 is 1 comma 2, now you just need to say p2 equal to p1. Entire p1's elements values will be copied to p1. p2's sorry p1's elements values will be copied to p2. Now you may ask, what if there is an array inside a struct, like earlier name is a character array or ID is a character array. So if I say student 1, student 2, if I want to copy all student 1's details to student 2, will it copy this array also? Name, ID, all these will it copy? Yes, it will copy everything. Every attribute, and even if that attribute is an array, every element inside that array, it will copy to the other struct. So it will do a deep copy. It's not a shallow copy. It's a deep copy. If it is a tree, it will copy until the last leaf. Everything here, it will copy there. So it is much easier to copy an array in a struct to another array in another struct rather than copying a separate array to an array. Right? That's it. So it's as simple as that. Copying one struct to another. Okay. Now, the next thing is structs can also be inputs and outputs of a function. The way we give data types as input and output to a function, struct can also be given as input and it can also be returned as output, right? Again, quite simple. So let's define a function called converse that takes a point as input. So point in the sense xy coordinates it takes, and it returns the converse sign. So if it is positive, it will make it negative. If it is negative, it will make it positive. Converse sign of each coordinate. Okay. So I will pass the entire point as input to this function. Struct point p. Right. In the function, what will I do? I'll say p dot x equal to minus p dot x and p dot y equal to minus p dot y. All right. And then so let us right now let us not return anything. Okay, let's say the return type is void. Fine. Now let us use this in a function. Yeah, use this in the main function. Call this function in the main function. So we say int main. Assume struct point is defined already. I won't repeat the definition. So I'll say point p1 equal to 1 comma 2, and then I will say print p1 dot x. What will it print? 1. p1 dot y, it will print 2. Now I pass this point p1 to the function converse. Okay. Now if I print p1 dot x, what will it print? 1 or minus 1? What will it print? It will just print 1 because this is a copy. This is not being passed by reference. This is being passed by value. So this p is a copy of p1. So whatever is being replaced here, only the copy is being changed. The original remains the same. Okay. So even if you print it, p1 dot x, here again you will get 1. p1 dot y, here again you will get 2. Okay. So to change it, to replace the original, one way is you pass the pointer, not the copy. Another way is you pass the copy, change the copy, and return the copy. Okay. So first we will apply this second method. So we will return p. All right. Then what should be the data type here? Struct point, right? Okay. And what should I do here? Yeah, P1 equal to, you are returning the point, store that return point again in the same point. So you are replacing the original point with the changed copy. Now you will get -1 and -2. Okay. You see, in the previous case, we didn't return anything. Whatever changes we made, they were left there in the function itself. Now we returned that value and we caught that value and we stored that value in P1. So now P1's values are replaced with the values inside the function. That's it, right? Okay. So now let us try to pass the pointer. All right. So before that, first let's look at how a struct pointer looks. Again, quite straightforward, nothing difficult. Suppose I say, in all these cases, you need to assume struct point is defined already. Okay. Let us give, and it also has an alias, say point. So let me say point P1 equal to 2, 3. Now I want to define a pointer to this struct point. Okay. So how do I do that? For an integer pointer, how do you write? Int star, say P equal to, you have int x, and then you say int star P equal to ampersand x. Same thing here. You have point P1. Now what should you write? How do you declare the pointer? Point star, say PTR equal to ampersand P1. That's it. Quite straightforward, right? Now, say if I print P1.x and P1.y, I'll get values 2, 3. Same thing, I can print using pointer to the struct. This pointer also can access these values, right? So how do we write that? Print P1 arrow x and, sorry, not P1, PTR arrow x and PTR arrow y. This will also print 2, 3. So if you are accessing the members of a struct through a pointer, then you need to use the arrow operator, not the dot operator. You can use the dot operator if you are using the struct name directly. But if you are accessing the members through the struct pointer, then you need to use arrow operator. Okay, P1 is name of struct. It's not a pointer to the struct. So you can just say P1.x, P1.y. But PTR is not the name of the struct. It is a pointer to the struct. So you need to say PTR arrow x and PTR arrow y. Now this is actually, these are equivalent to, can you guess what is this equivalent to in terms of P1? Star P1. P1 is what? How do I get P1 from PTR? See, what is the relation? PTR and P1. From P1, how do I get PTR? Ampersand. From PTR, how do I get P1? Star. So P1 is equivalent to star PTR. That's all. So P1.x means star PTR dot x. That's all. Similarly, PTR arrow y is nothing but star PTR dot y. That is P1.x and P1.y. That's all. Okay. All right. Now let us redefine our function by passing this struct pointer. So we'll say converse struct point. What do I write? Struct point star, say PTR. And now how do I perform the converse of the coordinates using PTR? PTR arrow x equal to minus PTR arrow x. Similarly, PTR arrow y equal to minus PTR arrow y. Do I need to return anything? No, the original values have changed. I need not return anything. So void. That's it. So now in the int main, all you need to do is say point p1 equal to 1 comma 2, and we need to declare, so this is point, we need to declare its pointer. Point star PTR equal to ampersand P1, and then why do we need again P1 equal to converse of? Only converse. Converse, what do you pass? What do you pass? PTR. PTR is the pointer to P. You need to pass a struct pointer. PTR is the pointer. Pass it. Otherwise, if you want to pass it in terms of P1, what do you pass? Ampersand P1. Address of P1, pointer to P1 means what? Address of P1. So either you pass ampersand P1 or you pass PTR, because PTR is nothing but address of P1. Right? That's all. Anything will work. Now if you print P1.x, you will get -1, and P1.y, you will get -2. So here you can either pass like this, or you can also pass converse PTR. That's all. So the original values themselves are changed. So you need not return anything. Okay. Yeah. So this struct pointer is a very important concept, because this will be the beginning for linked lists. In the next course, data structures, you will be starting with linked list. And linked list is nothing but a series of nodes. Each node is a struct node, and each node will be pointing to the next node. So why do we need a linked list? Multiple reasons. An array, like I said, it can be stored only in consecutive cells of the RAM. You cannot have an array distributed at different places in the RAM. Some elements here, some elements there, some elements somewhere else. You cannot have an array like that. It will not even allow you to create an array like that. If it has no space, it will say no space to create such a big array. Okay. So in case, suppose you don't have space, then what do? You store some element. You don't have continuous space. Then you have some pockets of spaces at different places. So you store some elements here, some elements there, some elements there. But how do you know all these elements belong to the same list? The only way is you link the addresses of these to each other, which means each node here will store two things. One is the data, say elements, say 4, 10, -2, and so on. So each node has the number which it is storing, and it is also storing the address to the next node. So two elements it is storing. Okay. So now it doesn't matter wherever they are. I can access the next node from the current node and its next node from the next node and my previous node or current node from the previous node. So every node, if I have address of only the first node, I can access all the other nodes. That's all. But the only disadvantage is you have to go through all the intermediate nodes to reach a node. In the array, it is the other way around. You can jump to any element because you know the number, you know the address. You can calculate the address. If it is 10th element, if it is a 10th integer, it is like base plus 10 into 4, 40. Base plus 40 will give you the address of the 10th integer. You directly jump there. You need not go through all the 9 integers in between. If you have million integers also, you can directly go to the millionth integer in the array. You need not go through all the million integers in between. But in a linked list, if you have to go to the millionth element, you have to go through all the previous elements, all the previous million elements. Because each element is accessible or its address is known only to the immediate previous element. First element does not know the address of millionth element. It knows the address only of the immediate next element. That knows the address of only immediate next element. So you have to go element by element to access any other later element in the linked list. But then if linked lists are so laborious and they are also occupying more data, you're storing two things for each element, the element and the address. So it's like double the memory. So why are you doing this? It is because if your data is dynamic, if it is growing and I mean you are adding elements, deleting elements, adding elements, deleting elements. So here it is very dynamic, right? In that case, linked list is better than an array. In an array is mainly better used for static data. If you know your array size is fixed or your list size is fixed, it's better you go with arrays. But if you don't know your list size is fixed or not, some more members are being added, some previous members are being deleted, constantly changing, the order is being changed, all these things. In that case, linked lists are better. Okay, anyway, you will learn more of these things in the next course. Yeah, so technically we are sort of done with struct. In the next class, I will spend maybe first 5-10 minutes on a couple of more things about struct and also some miscellaneous things which I could not cover in the course before. These are random things. They are not linked to one big topic or specific topic. Some random things which I wanted to cover, I'll cover. And if time permits, I will also discuss last year's EndSum paper so that you will get an idea for this EndSum. Okay. So let's stop here.